Have you ever mixed two clear solutions together and boom, a solid suddenly appears out of nowhere? That solid is called a precipitate, and predicting when it forms is one of the most important skills in chemistry. In this video, we're going to break down two key ideas that make this possible. Solubility rules. This will be your shortcut to knowing what dissolves and what doesn't. And net ionic equations, the cleanest way to show what's actually happening in a reaction. By the end of this video, you won't just be memorizing rules, you'll be able to predict reactions and write them step by step like a pro. All salts are not soluble in water. A salt will always precipitate when its ion concentrations are made larger than its solubility allows in a saturated solution of the salt. Generally speaking, if something is soluble, then we get an appreciable amount of the substance being dissolved. So the example I'm giving here, 1 gram or more solute dissolves in 100 grams of water is said to be soluble. And we're going to say that everything less than that, even slightly soluble or insoluble, we're going to treat those as insoluble. Okay, let's go through some of the soluble compounds in water. All compounds with alkali metals, which are group 1 metals, are soluble. All salts containing ammonium, nitrate, nitrite, perchlorate, chlorate, chlorite, and acetate are soluble. All permanganates are soluble. All dichromates are soluble. The next one you need to memorize. All chlorides, bromides, and iodides are soluble except when combined with silver, lead 2, and mercury 1. All sulfates are soluble except those of silver, mercury 1, mercury 2, calcium, and we're going to treat strontium, barium, and lead also as not soluble. Thiocyanates have the same rule as chlorides. I would suggest becoming very familiar with these rules. A list of the insoluble compounds. All hydroxides and all metal oxides are insoluble except for those of group 1, ammonium, and calcium, strontium, and barium. That's the bottom of group 2. All compounds that contain phosphate, carbonate, sulfite, and silicate are insoluble except for those of group 1 and ammonium. The rule for sulfides is the same as for oxides and hydroxides. All oxalates are insoluble except group 1, ammonium, iron 3. We're going to consider magnesium as insoluble. All chromates are insoluble except for group 1, ammonium, magnesium, calcium, and copper 2. Most fluoride salts are insoluble, with the primary exceptions of those of alkali metals and ammonium. Net ionic equations are used to denote reactions that are occurring in solutions. This is the most preferred because we're ignoring all the things that are just not actually participating in the reaction. All gases, solids, and pure liquids are written as full formulas. You cannot break those apart. Weak electrolytes in solution are primarily molecular, so they're written as full formulas also. Generally, weak acids and bases are weak electrolytes. Strong electrolytes are written as ions in solution. Generally, strong acids and bases are strong electrolytes. I would suggest memorizing this list of strong acids and strong bases. Ions which appear on both sides of the yield sign are called spectator ions, and they're canceled out or removed from the equation. Since they're not actually participating in the reaction, they're just spectating or watching. Soluble salts behave as strong electrolytes, which means we'll break those apart into ions. When writing net ionic equations, we cancel out the spectator ions and write what is left to give the net equation. Always be sure any two species that you cancel are in the same state, such as solid, liquid, gas, or aqueous. Reactions where water is formed tend to run to completion even though one of the reactants is insoluble or a weak electrolyte. By the removal of the water, the reaction is forced to continue. Reactions that produce a gas can drive a reaction to completion because the escaping gas cannot be used to reconstitute the reactants. Reactions that produce a weak electrolyte tend to go to completion because the formation of the slightly soluble product removes the associated ions from the solution. Remember to decompose unstable compounds that are given as products. So whenever you see hydrogen carbonate or carbonic acid, hydrogen sulfide or sulfurous acid, and ammonium hydroxide as a product, remember to always decompose them. For example, hydrogen carbonate will break apart into water and carbon dioxide gas. Hydrogen sulfide will break down into water and sulfur dioxide. And ammonium hydroxide will decompose into water and ammonia. If all ions cancel, then write no reaction for that example. So let's take these two reactants and let's go ahead and write a full equation. Okay, so I'm going to that would be RbOH, okay, plus HCl. Okay, so rubidium is going to go with the chlorine, so it's going to be rubidium chloride. And the H and OH are going to go together. Okay, so now let's look and see which ones are soluble. Okay, this is a group 1. All group 1s are soluble. This is a strong acid. It is soluble. A salt containing a group 1 is soluble. And this is a pure liquid. All right, so let's break these into ions. So I'm going to dissociate the first one. So it's going to form a rubidium plus 1 aqueous ion. I'm going to have a hydroxide aqueous ion. The HCl is going to ionize into a hydrogen aqueous ion and a chloride aqueous ion to produce rubidium chloride. Will dissociate into rubidium aqueous ion, a chloride aqueous ion, plus water as a liquid. Okay, let's go through and let's mark out our spectator ions. Rubidium is the same on both sides, so I'm going to cancel out rubidium. I notice that chloride is the same on both sides, so I can mark out that one also. So my net reaction will be a hydroxide aqueous ion plus a hydrogen aqueous ion to produce H2O liquid. This is called the net reaction, or net ionic reaction. This is showing what is primarily going on in the reaction given above. Okay, calcium chloride and sodium carbonate. calcium chloride, sodium carbonate. Okay, they're going to switch partners, so it'll be calcium carbonate and sodium chloride. Okay, now let's balance this. I know that all chlorides are soluble except for silver, mercury, and lead, so this is soluble. This has a group 1, so I know it's soluble. Okay, this one is insoluble because carbonates are generally not soluble. And this one is soluble. All right, so let's dissociate these. So I get calcium 2 plus aqueous plus 2 Cl negative aqueous plus 2 Na plus aqueous plus a carbonate aqueous. It's going to produce calcium carbonate, which is a precipitate, so it's going to be a solid, plus 2 sodium aqueous plus 2 chloride aqueous. Okay, let's try to identify any spectator ions. I have sodium, 2 sodiums, both aqueous, so they cancel. I have 2 chlorides that will cancel these 2 chlorides. So a net reaction will be calcium 2 plus aqueous plus carbonate 2 negative aqueous to yield calcium carbonate solid. So this is the net reaction. In the next reaction, we have calcium carbonate and sodium chloride. Calcium carbonate, sodium chloride, produce calcium chloride and sodium carbonate. Okay, let's balance the equation. Okay, this one is insoluble, soluble, soluble, and soluble. Okay, so I'm going to put NR, no reaction. And the reason there's no reaction is, for this reaction to go forward, I had to have something on the right side, such as a gas, a liquid, or a solid. And so I do not have any of these to push the reaction forward or to drive it forward, then it's going to be no reaction. Okay, the next reaction, I have ammonium carbonate and hydrochloric acid. So ammonium carbonate plus hydrochloric acid. So it's going to produce ammonium chloride plus H2CO3, a carbonic acid. All right, so this is soluble. All ammonium compounds are soluble. Strong acids, soluble. Soluble, ammonium compound. And this is a weak electrolyte. So I have 2 ammoniums, aqueous, plus a carbonate. Okay, I need to balance this, don't I? Okay, so I need a 2 here and a 2 here. All right. So I have 2H plus aqueous plus 2 Cl negatives, aqueous, from 2 ammonium, aqueous, plus 2 Cl negative, aqueous, plus H2CO3. All right, I'm going to further break this apart into water and carbon dioxide. Water is a pure liquid, carbon dioxide is a gas. So my net reaction, after canceling out my spectators, all right, so ammoniums cancel on both sides, and my chlorides cancel on both sides. Those are my spectators. So my net reaction, I'll put it right here. So it's going to be CO3, 2 negative, aqueous, plus 2 H plus aqueous, yields H2O, liquid, plus CO2, gas. So that's going to be my net equation. Okay, strontium chloride plus potassium sulfate. So strontium chloride, potassium sulfate. That's going to make strontium sulfate plus potassium chloride. Let's put a 2 here to balance it. All right, soluble, soluble, insoluble, soluble. So a full ionic equation would be Sr2 plus aqueous plus 2 Cl negative aqueous, 2K positive aqueous, SO4, 2 negative aqueous, SrSO4 solid, 2K plus aqueous, and 2 Cl negative aqueous. Spectator ions will be chloride and potassium. So my net equation will be strontium 2 plus aqueous plus sulfate aqueous, SrSO4 solid. Okay, so acetic acid plus sodium carbonate will give me H2CO3 plus NaC2H3O2. Okay, let's balance it. Okay, here I have a weak electrolyte. This is soluble. This is weak acid. And this is soluble. Okay, this weak acid here will drive the reaction forward, even though I have a weak electrolyte on the reactant side. So we have to keep it whole. All right, we'll dissociate the sodium carbonate. Carbonate. Aqueous. Can't have this on the right hand side as a product, so I had to break it down into water and carbon dioxide. Gives me 2 sodiums, aqueous, and 2 acetates. Okay, marking out my spectator ions. I have 2 sodiums. Okay, so that's the only spectator I have is my sodium. So my net equation is going to be so I have a liquid plus CO3, 2 negative aqueous to reduce water, so liquid, plus CO2, that's a gas, plus 2 acetates. Aqueous. So that would be my net ionic equation for that one. Potassium hydroxide plus ammonium bromide. Give me potassium bromide and ammonium hydroxide. Okay, I cannot have this as a product because it's too unstable. So it's going to break apart into ammonia and water. All right, this is soluble, soluble, soluble. So I would have potassium aqueous plus hydroxide aqueous plus an ammonium aqueous plus bromide aqueous to produce potassium aqueous plus bromide aqueous plus ammonia gas plus water liquid. So marking out my spectator ions, I would mark out potassium and the bromide. So the net reaction will be hydroxide plus an aqueous ammonium to produce ammonia gas plus water liquid. Okay, phosphoric acid plus ammonium hydroxide to form water and ammonium phosphate. Okay, let's balance this. There's 3 here, 3 there. Okay, so I have a weak electrolyte or weak acid. this is soluble, this is going to be a liquid, and this is soluble. So I'm going to keep this weak acid whole, so it'll be H3PO4 plus 3 NH4 plus aqueous plus 3 hydroxides produce 3 waters as a liquid plus 3 ammoniums plus a phosphate. Okay, let's mark out the spectators. I have ammonium on both sides. Okay, that's my only spectator. So I need to put liquid here. Forgot to put that. All right, so it's going to be H3PO4 liquid plus 3 aqueous hydroxides to produce 3 waters plus a phosphate. So that will be the net ionic equation for this example. All right, copper 2 iodide and ammonium sulfate. So that'd be CuI2 so it's going to give me copper 2 sulfate plus ammonium iodide. Let's balance it. Okay, soluble, 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 and soluble. No reaction because everything is soluble all the way across. All right, so let's recap what we learned. You now know how to use solubility rules to predict whether a compound will dissolve, identify when a precipitate forms, write a net ionic equation by removing spectator ions and focusing on their real chemistry. This is a huge step forward because these skills show up again in equilibrium, acids and bases, and electrochemistry. If you found this helpful, make sure to like and subscribe to the video, and I'll see you soon in the next video. Thank you again.